Hello, in this video I'm going to work through the practical analysis task from March 2017. This is part of the Unit 5 practical examination with the WJEC. The first question tells us we have a snooker ball with a density of 1700 kilograms per meter cubed with an uncertainty of plus or minus 40 kilograms per meter cubed. Its diameter is 52.6 plus or minus 0.1 millimeters, and we're asked to calculate the mass of the ball along with its absolute uncertainty. So first thing we're going to do is work out the volume of the ball using 4/3 pi r cubed. That formula is in the back of the data book if you forget it. Now the diameter is 52.6, so the radius is 26.3, but it's millimeters, so we convert to meters and remember to cube it. And then we end up with 7.62 times 10 to the minus 5 meters cubed. To find the mass, we can multiply the density by the volume. 1700 times the 7.62 times 10 to the minus 5. And that will give us 0.130 kilograms. Now, to work out the absolute uncertainty of this mass, we first of all have to work with percentage uncertainties. So first of all, I'm going to calculate the percentage uncertainty in the density by taking the absolute uncertainty of 40, divided it by the value of 1700 and multiplying by 100 to get ourselves a percentage. Now that comes out as about 2.4%. Now remember, never give uncertainties to more than two significant figures. Percentage uncertainty in the radius will be exactly the same as the percentage uncertainty in the diameter, because to get the radius all we've done is divided the diameter by 2. So the percentage uncertainty in the radius is 0.1 over 52.6, and again times 100 to convert that into a percentage. That's quite a small one, it's 0.19, so I'm just going to go with 0.2% just to match the first decimal place that we had for the uncertainty, percentage uncertainty in the density. The percentage uncertainty in the volume will be the same as the percentage uncertainty in r cubed, which will be 3 times the percentage uncertainty in r. Whenever we raise a quantity to a power, its percentage uncertainty is multiplied by that power. So the percentage uncertainty in the volume is 3 times 0.2 or 0.6%. Now therefore, the total percentage uncertainty in the mass will be the percentage uncertainty in the density plus the percentage uncertainty in the volume. And if we add those values together, we've got 2.4 plus 0.6, which is 3.0%. To find the absolute uncertainty in the mass, we now simply find 3% of the 0.130 kilograms that we worked out in the very first part of our calculations, a little bit later on in the calculation, and that to one significant figure is 0.004 kilograms. And because it's a final answer, my advice is to write it to one significant figure. You could theoretically write it to 2, but certainly no more than 2. So if you went for 2 significant figures, you get about 0.038 roughly kilograms. So finally, I'm just going to state that the mass is 0.130 plus or minus 0.004 kilograms. And note that I certainly wouldn't round this 0.130 just to 0.13. The 0.004 is the third decimal place, so we would leave our mass to the third decimal place as well. For question 2 rather, Katrin investigates how the discharging of a capacitor through a resistor depends on the initial potential difference applied across the resistor. And we've got to draw a circuit diagram for that investigation. So what we have is a power supply. We have the capacitor that we're going to charge up by connecting it to that power supply. And we're going to need a switch here. And we're going to have the resistor connected in parallel with the capacitor. We could add a switch in the bottom part of the circuit, but we don't actually need to. We need one more thing because we're investigating the potential difference, so we're going to connect the voltmeter, and so long as it's anywhere in parallel with the capacitor or the resistor, then that will be fine. Next, Catherine performs another investigation, so we're ignoring that diagram that we've just done. She investigates how the energy stored in a capacitor depends on the potential difference. And the relationship between the energy in the capacitor U and the PD across it, V, is expressed as U equals KV to the N, and K and V are constants. So we've got to explain which graph should be plotted to determine K and N. So here we're going to realise that we're going to need to take logs. So if we take logs, we've got log of U is log of K times V to the N. If we take logs of K times V to the N, we get log of K plus N log of V. And if we compare this to the equation for a straight line graph, y equals mx plus c, or c plus mx here, we can see that we're going to plot log u on the y-axis and log v on the x-axis. And later on we're going to use the fact that the gradient will be n and the intercept on the y-axis will be log of k. This is enough. We could write down a sentence here that says plot log u on the y-axis and log v on the x-axis, but this sort of linking of y's and x's to log u and log v is fine for the examiners. Next, we've got Catherine's results. We have a table of potential differences and mean energy stored, and we've got to use our answer to B1 and the above data to obtain suitable values to allow us to plot the graph. So what we're going to do is we're going to create a table which is log of V, which has no units, and log of U, which also has no units. Logs don't have units. So I've already plugged these into a calculator, so you can check them yourselves, but I'm going to fill them in. But remember that when you're doing these, make sure that you are very careful with rounding. You will lose marks if you incorrectly round any of the answers. Now I'm doing all of these log V's to 3 significant figures or 2 decimal places. That way I can pretty much guarantee that I can plot them accurately on the graph. There's no point in doing any more significant figures because I wouldn't be able to get any more than that final decimal place. Similarly, I've done the log U values. I'm going to put all of these to 2 decimal places as well. We need to be consistent with decimal places. We don't mix them, or that will cost us a mark. And make sure, of course, that you write down things like 3 as 3.00 and 4 as 4.00. Next, you've got to plot the graph. Now I've gone ahead and done this in advance. The scale I used horizontally and vertically was to use each of the major squares, the major divisions being worth 0.4. I've labelled the axes with log of V and log of U with no units, and I plotted the points. Now, a couple of points about drawing the graph. You've got to make sure that your points occupy at least half of the graph paper. So looking in the vertical direction, you can see quite easily that we've covered almost all of the paper. Horizontally, our points have covered 1, 2, 3, 4 and 5 for the last one, 5 squares. The rule that was explained to me by the examiners at the last conference I was at was this: making sure that you occupy at least half of the graph paper rule is interpreted by them as that you have points in at least half of the squares. So looking horizontally, we have 1, 2, 3, 4, 5, 6, 7, 8 squares available, and we got points in 1, 2, 3, 4, 5. So 5 out of 8 will satisfy that criteria. Each point needs to be plotted as accurately as possible within one half of a small square of where it should be. So take care in plotting the points, and then make sure that you do a good line of best fit through them. So if you're missing points, try to have a few points above the line and a few points below the line, and go ahead and plot that. I've also extended a line a little bit. I've marked this top ordinate as 4.7 on the log U axis so that I can find the gradient of this line in a moment by using a very large triangle. Part D in fact says use your graph to determine n. So let's make a statement that n is the gradient. And if we take the values that we've got off the graph, the change in y is 4.7. over the change in x, 3.5 take away 1.2. Now if we put those values into the calculator, we end up with an answer very, very close to 2. In fact, I got 2.04. Next, theory states that the equation for the energy stored by a capacitor can be expressed as U equals a half CV squared, and we could explain whether our value for N from part D is consistent with the above equation. Well, the original equation was U equals KV to the N, and if we compare these two, the power of V should be 2. And the value that I got is near enough 2. So in other words, we got a value for N that is consistent with the above equation. For the final part of the paper, Catherine has used two 100 millifarad capacitors connected in parallel with an overall tolerance of 10%. We're going to determine whether this is consistent with your graph. Now remember that capacitors in parallel add up, so the total capacitance should be 200 millifarads plus or minus 10%, so plus or minus 20 millifarads. If we go back to our comparison with logs right at the start of this, we saw that the y-axis intercept is equal to log k. Now unfortunately, the way we've drawn the graph, we can't read the y-axis intercept. It would actually be something sort of fairly negative on the graph there. So what we're going to do is a method where we take a reading off the graph, substitute the values for log u, log v and n into this equation and solve for log k. So let's rewrite that equation. Log of u is log of k plus n log v. And let's take some values off the graph. So let's go with, for example, here the 2.5 value for log v, going with near enough 2.65 for log u. I'm going to take n as 2. So we have that log of k will be 2.65 minus 5. The 2 times 2.5 is 5. So log of k will be minus 2.35. And k then will be e to the minus 2.35. And that will give us 95.4 times 10 to the minus 3. Now I've done it as times 10 to the minus 3 because that's milli and we were talking about millifarads in the question there. So theoretically, going back, comparing our equation u equals kv to the n to u equals a half cv squared, we can see that k should be a half c. And therefore c will be 2k. And that will give us about 191 millifarads. And that is within the range that we're expecting here. We said that the capacitance should be 200 plus or minus 20, and 191 is just 9 below the 200 there. So let's just put a last little comment there. So consistent with the supplied capacitances, or capacitors if you like. Okay, so that's the end of that paper. Went through it quite quickly, but in reality the thing that takes the most time is getting this graph right. So think carefully about scales, plot points carefully, make sure that we label axes, draw a consistent line of best fit and find that gradient. So once again, thank you very much for listening. Please remember to like and subscribe, and feel free to leave any comments. Goodbye.